Almost every metal has a unique reaction with mercury, and a couple of months ago, I decided to make a series about it. For the first video, I started with sodium metal, and I combined it with the mercury by just dropping pieces in and then squishing it down. The reaction that occurred was extremely fast, and it also generated a lot of heat. This caused the sodium to melt almost instantly, and sometimes it also splashed and ignited. Most of the sodium was dissolved though, and the concentration of it in the mercury slowly rose. When the concentration was below about 1%, it stayed as a liquid, but as it got above that, it started to solidify. I decided to make both of these forms, and in the end I was left with this, which still kind of just looked like regular mercury, as well as these solid amalgam crystals. Now, the reason that I started this series with sodium wasn't just random, and it's because the sodium amalgam can be used as a gateway to other amalgams, especially to those that are normally difficult to form. One in particular that caught my eye was the ammonium amalgam, which I first read about on Wikipedia. The reason it stood out to me was because unlike all the other ones, ammonium isn't a metal, at least under normal conditions. I really wanted to try making it, and I found a paper from 1865 that outlined the general process. It unfortunately didn't give exact details on how to repeat it, but it was enough for me to get started. It said that the liquid amalgam often worked better, so I decided to try that first. So using a syringe, I pulled out a small amount of it, and I added it to another vial. Then into this, I poured in some 10% ammonia solution. This was done just to see if it would have any reaction with the ammonia. It seemed to be pretty much the same as with pure water though, and nothing too interesting was happening. The sodium in the amalgam basically just reacted with the water to make sodium hydroxide and hydrogen gas. To form the ammonium amalgam, I had to convert the ammonia, which is NH3, into ammonium ions, which are NH4+. One easy way to do this is to just add an acid like hydrochloric acid. Almost immediately, the ammonium amalgam started forming, and it all puffed up. Now, as far as I know, what's going on here isn't really known. The general idea, though, seems to be a redox reaction between the sodium and the ammonium ions. The sodium metal really wants to give up an electron, and the ammonium ions, which are positively charged, are willing to accept it. This causes the ammonium ions to lose their charge and become neutral, and for the sodium metal to become sodium ions. These sodium ions are quickly pushed out of the mercury, and they combined with the chloride anions in solution to make sodium chloride. The ammonium radical, however, which is now neutral, seems to dissolve into the mercury. In its normal ionic form, this would never happen, but it's believed that as a neutral radical, it might act similarly to sodium metal. It appears to be able to easily diffuse through the mercury, but it isn't very stable. So almost as quickly as it forms, it starts breaking down into ammonia and hydrogen gas. In general, mercury tends to repel most things that aren't metal, and gases usually pass right through it. But in this case, it was somehow solidifying, which let it hold on to the gas. Again, unfortunately, it has never really been proven what's happening here, but I feel like it's probably one of these two possibilities. The first one is that, like sodium, a small amount of the ammonium radical might be able to solidify mercury. And if that were the case, it might even be possible that it could do it at a lower concentration. The other possibility is that the distribution of the sodium in the mercury is somehow altered by both the reaction and all the bubbles that are being produced. Some of the sodium amalgam might be shifted around, and it could cause some areas to have an increased concentration. And in theory, especially because I already started with a 1% amalgam, a slight increase in concentration could cause parts of it to start solidifying. For example, if we look back to when before any of the acid was added, all of the bubbling was already causing some weird rippling effect on the surface. And in my opinion, I thought this kind of looked similar to the texture of the ammonium amalgam. These are just some of my ideas though, and of course, they could be wrong. So I'd really like to know what you think in the comments, and whether you agree with me, or maybe if you have some sort of theory of your own. But anyway, after doing this a few times, I noticed something. In all these runs, I let the sodium amalgam bubble for a while, but if I added the acid right away, the results were different. Instead of a nice and smooth expansion like the other ones, it would really look like it was struggling. The other times, after adding the acid, it took about 5 seconds for it to start floating, but here, it took closer to 20. It also had a much harder time holding onto the gas, and it took a lot less time to turn back to a liquid. Okay, so now that I had some sort of idea of how it all worked, I wanted to try experimenting with it. As we saw before, the amalgam that formed was relatively unstable, and it quickly started degrading into hydrogen and ammonia gas. Everything that I'd done so far was at room temperature, but according to that paper from 1865, the degradation could be slowed down by keeping it cold. To do this, it was pretty simple, and I just had to put a small bottle of 10% ammonia in some ice. I let it sit there for something like 20 minutes, and after this, the general procedure was the same. The first difference that I noticed was at this lower temperature, the sodium amalgam in the water didn't really react very much. I then added the acid, and the reaction here was quite a bit slower as well. In the other runs, it usually took about 5 seconds from the first drop for it to expand enough to make it float. But this time, it consistently took around 10 seconds. The sponge that initially formed seemed to be smaller, and it took longer to expand to its maximum. I initially assumed that this would make it last longer, but that didn't seem to be the case. I figured that a good endpoint was when the thing sank back down to the bottom, and in every run, whether it was cold or at room temperature, it took almost exactly 2 minutes to do this. This really surprised me because I assumed that the colder one would have lasted a lot longer. But anyway, from this, it appeared that keeping it cold or letting it pre-expand at room temperature were both decent ways to make the amalgam. The lower temperature slowed things down a lot, and it allowed me to add the acid right away. However, the expansion was a lot slower, and I think I actually liked it when it went faster at room temperature. The next thing I wanted to do was to get it out of the vial and to take a closer look, but of course, it wouldn't fit out the top. I would have had to squish it down or wait for it to shrink, but both of these options were pretty bad. The only reason that I was doing it in a vial, though, was because it was easier for you guys to see. So the very simple solution to this is to just sacrifice the visuals a bit and to instead do it in something open, like a test tube. For this run, I did it on a slightly larger scale, and I also used cold ammonia because now that was just what I had. The moment that it stopped growing, I poured out the water and I dumped it onto some paper towel. It started degrading really quickly, and I thought that this was because now, without the water, there weren't any ammonium ions to help keep it alive. To test this, I tried adding some pre-made ammonium chloride solution, but it wasn't able to rescue it. I then started poking at it a bit, and it was way softer than I expected. It didn't last long in this semi-solid state though, and over the course of about 30 seconds, it went back to being mostly a liquid. After a couple minutes of sitting there, it got coated with a white solid, which I imagine was a sodium-based salt. Maybe something like sodium chloride, sodium hydroxide, or sodium carbonate. I tried adding more ammonium chloride solution, but as I kind of expected, it didn't grow. However, there was something weird happening on the surface, which I thought was interesting. I'm not exactly sure why this happened, but over the course of the next couple minutes, the effect slowly changed. When the bubbling had almost completely stopped, I tried adding more ammonium chloride, and it split the drop, which was kind of weird. Regular mercury would just do something like this and completely repel it, so its surface tension had obviously been messed up a bit. I think this might just be caused by some residual sodium that's left over, but I'm not really sure. The next thing I wanted to try was to do things the opposite way, which was adding the sodium amalgam to a solution of ammonium chloride. This was made by quickly adding some 10% ammonia, followed by a random amount of acid. I mixed it around, and then I added some drops of the amalgam. It turned out pretty much exactly as I expected it would, but I thought it was still kind of cool. So far, everything had been done underwater, but I wondered how it would look without all the liquid. So I put some sodium amalgam onto a watch glass, and I added some pre-made ammonium chloride. This time, instead of puffing up, it stayed a lot more flat, and I thought that it looked even more interesting than before. It didn't last nearly as long, but I figured that was just because it quickly used up all of the ammonium chloride. So once it had shrunk down again, I added some more. This did end up working, but it was a lot slower and it didn't stay flat like before. Now again, in that paper from 1865, he tested several different ammonium salts and they all apparently worked just as well. However, for some reason, ammonium nitrate seemed to destroy it. So I tested this by adding a dilute solution of it. The parts that it touched immediately started to shrink, and when I added a whole bunch, it murdered it. Just for good measure, I tried adding more ammonium chloride afterwards, but it didn't do anything. For the other tests, I tried cooling it down, but now I want to see what happened if I heated it. To do this, I just blasted it with my heat gun for a bit, and then I added the ammonium chloride. I'm not sure how hot I got it, but I think it was above 100°C because it sounded like some of the water boiled when it was added. The high heat also caused the amalgam to die almost instantly, and it barely grew at all. So I tried it again, but I didn't heat it for nearly as long. This time, I thought the reaction was a lot more interesting, but it was still really short-lived. I kept adding more ammonium chloride, and it went through a few more growing and shrinking cycles, but it eventually stopped working. I wasn't really sure what to do with it at this point, so I just tried blasting it with my heat gun. I thought that it would destroy it relatively quickly, kind of like when I added the ammonium nitrate. And not too surprisingly, it did cause it to decompose, but it wasn't nearly as fast as I thought it would be. Now I honestly don't remember why, but for some reason I decided to stop heating it and to try adding more ammonium chloride. The moment it was added, the bubbling slowed down quite a bit, and it kind of looked like it froze. However, I'm not sure if this was actually because of the ammonium chloride, or because the solution was just cold and it was cooling things down. After a couple minutes, it didn't really change in size, so I started poking at it. I honestly have no idea how to describe its texture, because it wasn't like anything that I've ever felt before. It was incredibly soft, and there was very little resistance when I pushed on it, but it was still strong enough to hold its shape. It did slowly degrade though, which was probably both natural and because I was constantly moving it around. Now the question is, why did it freeze like this, and why did this never happen with any of my other runs? And the answer, apparently like everything else in this video, isn't something that I know. Somehow though, it's still retaining a bit of its solid character, and it's also holding on to a bunch of the gas. It was a bit hard to tell here, but when I pushed away the surface layer, you can see that it was still filled with bubbles. Over the next few minutes though, it all went back to being a liquid. Okay, so that was everything that I tried with the liquid sodium amalgam, and now I wanted to do it with the solid one. I started by adding it to some ammonium chloride solution, but the effect was pretty lame. Even after leaving it for a couple minutes, it didn't really do much. What was much more interesting was when the solution was added to it, like I had just been doing. Because it was solid, it kept most of its shape as it expanded, and reminded me a lot of those toys that grow when you leave them in water. It very quickly maxed out in size though, and then just like all the other times, it degraded back to being a liquid. But anyway, I think this brings me to the end of the project. When I first started, there wasn't even a single photo of this amalgam online, and I didn't really know what to expect. However, it turned out to be even more interesting than I thought it would be. The debate now, though, is whether or not what's forming here is actually an amalgam. Over the years, several tests have been conducted which strongly suggest that it is, but as far as I know, it has never been confirmed. And unfortunately, I don't think many people are putting in much effort to find out. I'm personally on the side that some sort of ammonium amalgam does form, and hopefully, eventually we'll get a definitive answer.